Hi guys, and welcome to this video tutorial on using a digital multimeter. What we're going to do today is have a look at the three main functions of the digital multimeter, how we use it, and have a look at using it to read a few different things. So without further ado, the meter we have here in front of us is a Sealy TA203. However, most multimeters will have similar functionality to this. We also have a set of test leads here, and we're going to plug the test leads in as our starting point. And you will notice, although we only have two test leads here, we actually have the option of 4 different holes that we can actually plug that into. Now, our test leads are color coordinated, red and black, and to start off with, I'm going to separate those out, and I'm going to connect up the black lead into this port here. This is our common port, and if you have a look, you'll actually see that this will actually link up to the other 3 ports, which are actually red in color. So black one, our common, into there. The next thing we need to decide is what are we actually going to be reading. Now, if you remember when we were looking at volts, amps, ohms, and watts, we are going to actually be looking at how we can measure volts, amps, and ohms. Starting off with the most common one to use with a digital multimeter like this, it's probably going to be volts. And if we have a look at the scale here, we can see this port here is highlighted in volts, ohms, hertz, percent, RPM, capacitance. So I'm going to take my red lead, my second test lead, and plug that in to that scale there. Now, the next thing is we have a dial in the center, and that dial can actually be swapped around onto any one of these settings. The one I'm specifically interested in here is volts, so I'll just click that over onto volts and you'll see the screen. I'm just going to highlight that, bring the light on, there we go. Okay, so that's our volt scale. The other thing about this is the voltage scale actually reads all the way up to the maximum reading of this meter, which in this particular case, I'll just separate these out, and you'll see is 1000 volts DC just down there. I don't know if you can make that out on the video screen. Now the problem with that is it's going to take longer for the meter to give it a good reading if I leave it on that scale. So the first thing I always do with this style of meter is I use this range button, and I'll range this down to the type of scale that I'm going to want. Now, typically for automotive use, I'm either going to read down to 1/10 of a volt or 1/100th of a volt maximum. So by pressing this, we'll actually move the decimal place, and currently you can just see that's on millivolts. We actually want this to be on volts so we don't get confused when we're taking our reading. So here we go, I'm just going to press that. So now we can read 9.999 volts. Decimal place is there. We've got a volt reading on the screen there. Now we can read 99.99. But I'm going to go a step further and actually press it once more. So this would actually read the 999.9 volts. And this will stabilize a lot quicker for what we're going to measure. What I've got here now is I've got a very simple series circuit. We've got the components, a battery, a switch, a bulb, following through to a second bulb, and going back to a battery. As you remember from our lesson on circuits, the circuit here is currently broken because the switch isn't turned on. As soon as I turn the switch on, the lights will come on. So now that light's on, circuit's made and current is flowing around it. For the moment, what I want to do is just turn that circuit back off and take a voltage reading at the battery. I'm taking the red test lead, and I've already connected using this jump wire up to the common on the multimeter, and I'm going to put the red test lead on this side of the battery, which then gives me my battery voltage, in this case 6.3 volts. As I go around the circuit, I get 6.3. As I get past the switch, no volts, no voltage. And the reason for this is because the electrical pressure is stopped. So here we have battery voltage, same as here, 6.3, 6.3, nothing after, because this, remember our water analogy, this is like having a tap and turning a tap off. Let's have a look at our voltage readings with it turned on. Going to check battery voltage again. Slight drop, 6.2, 6.2, and after the switch, 6.1. Now that does mean there's a slight resistance in the context of the switch, and we're losing 0.1 of a volt. This is the premise behind volt drop testing that we spoke about. We'll also see, just change hands, we'll also see on the other side of the first bulb, the voltage has dropped substantially. We're now down to 3.1. The bulbs are almost the same brightness. We'd expect each bulb to be consuming half of the voltage. 3 volts, so there may be a little bit of resistance. 3 volts, 3 volts, 3.1. So on that connection there, we have a slight resistance, which is costing us another 1/10 of a volt. However, by the time we get down to the earth here, what we should see is a 0 voltage, as all the electrical pressure should be used up. Let's have a look. 0, exactly at what we predicted. So just finishing off there from the use of the voltmeter, one thing I do want to draw your attention to is the fact that you can see here that the red lead is not plugged in, but I do have a scale changing ever so slightly. There is a scale there. But if you look closely, you'll actually notice the MV, so millivolt scale, is on, and it's quite common just to see that jumping around. If I plug that back in and touch the two leads together, that should actually drop down to 0, like that. However, what I wanted to look at is our next scale, which is our ohms scale, our resistance scale. And if we see here, volts, our next one on is the omega symbol, ohms, and I'm just going to turn it onto there. And we get a reading of OL, or over limit. We haven't got the red lead connected at the moment, and so we still have our 3, and if you remember from before, these 2 are for amps, and if we look here, we can actually see the ohms signal, or sign, rather symbol I should say, just there. And so I'm going to plug the red lead into that. Currently nothing changes. However, if I take our 2 leads and touch them together, like so, you'll notice the scale actually changing, and it's gone all the way down, and it stopped at 0.2 ohms. 0.2, 0.3. Just dancing around a little bit. That is probably okay for most of the resistance testing that you're likely to do. However, if you want a more accurate reading, when you put the leads first together, holding them firmly, if you press this button here, the relative button will actually zero it. And so now that any resistance reading that we take will take into account the resistance of the two leads before we start. So going back to our circuit board, the first thing I'm going to do, I have changed the leads over. Now I've got the banana plugs here again. And the first thing I'm going to do is just check the resistance of this 12 ohm resistor. So we're still on the ohm setting. I'm putting that in there. We have our first reading. And you'll notice the reading itself isn't 12 ohms. In fact, once that stabilizes, that's settling down. We're talking 14.6, 14.7 ohms. Now that might seem like there's a problem. But the resistors themselves do have a tolerance. What I'll do is I'll post up a link showing you the tolerances of different resistors as far as accuracy is concerned. So hopefully that'll explain why the actual resistance value that we see on the screen is different to the one we've actually would expect to see based on the value of that resistor. Going to the two resistors mounted in series here, I wonder if you can remember exactly how we calculate the resistance or total resistance of a circuit when the resistors are in series. That's right, we add the two values together. In this case, we have a 10k, 10,000 ohm resistor, and a 1k, 1,000 ohm resistor, so the total value we're expecting to see would be 11,000 ohms. Let's take a look and see what value we get. So the value on the screen we've got is actually 10.88, but if you look closely at the top corner here, we have K, K meaning 1000, so this would be 10,880 ohms, which is pretty close to our 11,000 ohms expected, and again this is down to the tolerance of the resistors. Now the last thing we're going to have a look at as far as the multimeter is concerned is we're going to look at the amp reading. Now the reason I've actually left this to last is because amp reading is not something I like doing using this method. The reason for that is because it means breaking into the circuit. If you're fault finding, which is the only real reason for doing this, you could inadvertently fix the fault just by breaking into the circuit. Anyway, it is important that you know how to do this, so I'm just going to run through it. And there's also a problem that you can have with the multimeters that you need to be aware of whilst we're doing this. So as before, black wire is going to go into common in the middle there. This time, however, we're not going to use this port, we're going to use either this port or this port. Now in this particular instance there is a problem with the multimeter, so I'm going to use the 20 amp scale here. That's going to time me down on the dial here. I can't use micro or milliamps, I've got to go up to the 20 amp scale. So I'm going to turn the dial on, just bring the light on so it's easier to see, and I've got my amp reading ready to go. But to measure amps, what we need to do is we need to actually put the ammeter in series with the circuit. So what I'm going to do is remove one of the connectors and connect the ammeter in there. Notice as soon as I take that out, the light goes out, or both lights go out. And as I put these in, the light should come back on. And we get our amp reading on the screen there. And currently we've got 0.2 of an amp flying through this circuit. Out comes the bulb. You'll notice the amps drop down to 0. In goes the wire connection. And that bulb is a lot brighter. However, although the amperage has increased, it hasn't increased by as much as you might expect. You would expect it to go up double. However, because the actual light is that much brighter, there's more resistance in that bulb. More resistance means less current flow. And so whilst it is more than the two bulbs combined, it's not double what you might expect. So as I said, there is a problem with this particular multimeter. On this circuit here, the micro and milliamp setting, and at some point somebody's exceeded the capacity that the multimeter can cope with. Fortunately, just like most modern multimeters, there is a fuse inside it. And I just want to show you that so as you've got an idea of what might go wrong if you actually start measuring too high amperage on too low a setting. So what I'm going to do is I'm going to take the plastic cover off of the multimeter and just unscrew the back and show you where the fuses are located. Just going to turn it off. So I've turned it over there, and we can actually see there's two halves to this. And the case is screwed on just here. And I'll just get a Phillips screwdriver and take that screw out. There's the screw. Cover slides off. And we'll see under the back here, as I said, standard 9-volt battery. We have a large fuse that takes care of the 20 amp circuit. However, this fuse here, the smaller fuse, is actually blown. If I could check the 20 amp fuse, I can see there's virtually no resistance there. However, when I go over to the smaller fuse here, you'll see that the resistance doesn't change. It's over limits. And that's because the element of the fuse has actually blown because somebody's connected this up to too high amperage. In this particular case, all that fuse can cope with is 400 milliamps or 0.4 of an amp. Well, I hope you enjoyed that. I hope that was useful to you. And please complete the worksheets that are associated with this video. And I'll see you back in the classroom.